In our last lecture of lecture number 5, we showed that for any positive integer n and for something f of n equals to g of n. So in our current lecture, we also show a similar problem, which is one of the most important question for college level and university level examinations. So and also an important question to understand our earlier question and this question too. So initially, for those who already studied the lecture number 5, they firstly try by the statement. You can try following the path of last question, which was showed in lecture number 5. So now let's begin our lecture number 6. So here we are taking this side is f of m and this side as f of n. So we are g of m. So we have both f of n m and g of m. So initially in our early lecture and this lecture, both questions are quite similar to each other. So initially we have to show that what we have to show that f of m and g of n are multiplicative. To show that initially I can ask everyone a question that what is multiplicative function. A multiplicative function is that multiplicative function is must be an arithmetic function. That means f of m into f of n equals to f of m dot f of n is a multiplicative function, which is nothing but this one, f of mn, which is also told in our early lectures, dot f of n. So let's begin. So we have f of mn equals to summation this value, and we know that we can write d as the product of d1 dot d2, as we have that d1 divides m. So we can write there exists an n for that d1 divides m and d2 divides n. Here will be a n another. So we can replacing n as the product of mn and d as product of d1 dot d2, as we have that sigma of d1 of d2. That means if we write intentionally both d1 and m together and n and d2 together, then after we will have the another this way. And as we know that sigma is also a multiplicative function, then we can write sigma of d1 d2 as sigma of d1 and sigma of d2. So if we write intentionally the m d1 together and m n d2 together, then we'll have f of m dot f of n. That means f is a multiplicative function we showed. Now we have to show that g of m is a multiplicative function. So to show that g of m and g of m is a multiplicative function, so we are taking there is g as a product of g of mn. That means summation d divides, and it's not comma, it's product. That means d divides mn. That means d of tau of d. So d can be written in the, as I told earlier lectures and in this lecture too, that d is the product of d1 dot d2, and where d1 divides m and d2 divides n. So d can be written d1 d2 and this way. So here it is d1 dot d2 equals to tau of d1 and tau of d2, because tau is a multiplicative function, and it's the proof of this tau. The proof of tau is a multiplicative function in two separate ways are mentioned earlier. That means we can write if we write initially that d1 and tau d1 together and d2 and tau d2 together, then we'll have g of m and g of n. Therefore we can say that g is a multiplicative function. So in our we also till this we already proved that f and g are both multiplicative function. Then now we have to write it in the form of p raised to the power alpha. So we start our taking that if we write g equals to p raised to the power alpha, g equals to p raised to the power alpha in the form of d tau d. That means for tau of 1 and here it is written in the form of p tau of p, and similarly we are replacing the alpha values as 0 1 dot alpha. That means p raised to the power alpha, which is the value of p raised to the power 0, p raised to the power 1 dot p raised to the power alpha, which we have tau of 1 p tau of p square tau of p square and so on, and we have p square tau of p raised to the power alpha. We know that the tau of 1 are always 1, and another thing we have that tau of prime numbers are always 2. Here it is, and here we have p square and tau of p square. Tau of p square is nothing but the number of divisors of p square. That we wrote that we know that tau number of any numbers, tau function will be that means the power plus 1, 2 plus 1, that means here we wrote that 2 plus 1, and so on, and we have p raised to the power alpha, and the tau of p raised to the power alpha will be nothing but our alpha plus 1, which we have here. And now we have 1 plus 2p plus 3p square plus so on, and we have p raised to the power alpha and alpha plus 1. So if we write this intentionally in opposite form, rewrite this as this form, that which implies that alpha plus 1 p raised to the power alpha plus what will be the alpha plus alpha of p of alpha minus 1, which implies that the earlier number of this, and so on. And if we write another number, that alpha plus 1 p raised to the power alpha minus 2 plus so on, and in at last we have 2 3p square plus 2p plus 1. So we are taking the writing this as one number 1, and if we move forward to f of p of alpha, which is p of alpha by d and sigma of d, and p of alpha sigma of 1, and p of alpha by p into sum of d. D is replaced in the p of 1, and similarly sigma of p square, and at last we have sigma of p raised to the power alpha. So we all know that the sigma of one value are always equal, and sigma of p is nothing but our p plus 1. So here it is that p raised to the power alpha is as usual, and sigma of 1 is always equals to 1, and p raised to the power alpha by p, and sigma of p is p1 plus p, and it is written as usual, and we can write the p square as sigma is the number of sum of the divisors. So what will be the divisors of p square? The divisors of p square will be 1 comma p square itself, and where p is a prime number, and so sigma of p square will be the sum of the divisors, which is nothing but 1 plus p square, which is written here. And similarly so on, if we write the sigma of p raised to the power alpha, so p raised to the power alpha, the number of divisors will be 1 p square, p cube, and so on to p alpha. So if we write the sigma of p raised to the power alpha, then it will nothing but the sum of the 1 plus p square dot p raised to the power alpha, which is written here. So now we are as per our exponent's law, we are taking our denominator in numerator, and which can represent alpha minus 1, alpha minus 2, and so on. So we have p raised to the power alpha, p raised to the power alpha minus 1, p raised to the power alpha, and so on. So if we write the how many times p plus p to the p raised to the power alpha, we have that p raised to the power alpha we have at alpha plus 1 times, and how much times that p raised to the power alpha minus 1 we have that at alpha times we have that p raised to the power alpha minus 1. Similarly, how much times we have p raised to the power alpha minus 2, we have alpha minus 1 times. Similarly so on, we have p repeats for 2 times and 1 repeats for 1 times. So if we try to compare both the equation number, the polynomial number 2, and we have the polynomial number 1 itself, which we showed earlier, which are similar to each other. The polynomial number 2, which is f of p raised to the power alpha, and g of p raised to the power alpha, both are quite similar to each other. Not quite, it's similar to each other. So now again we can say that as f of and g both are multiplicative to each other, and we showed that the alpha extension of both f of p of alpha and g of p of alpha are similar. Therefore, by our known result, what was our known result? our known result was that f of p of alpha equals to g of p of alpha for all alpha belongs to natural numbers. Then we can also that natural whole numbers, that is natural numbers in union 0, then f of n equals to g of n. That means for all n, if f and g are multiplicative function, we can similarly says that f of n equals to g of n for all n belongs to positive integers. That means our statement of the question is proved now. So here we conclude our theory of tau of n, tau function, sigma function both, and we learned about various definitions, theorems, and many theories. So from our next lecture we will learn about Mobius function.